In this lecture, I want to derive the following formula. The sum, with the index n going from minus infinity to plus infinity, of the complex exponential e to the I 2 pi n x is equal to the sum, with the index n going from minus infinity to plus infinity, delta, Dirac delta of x minus n. So in order to derive this formula, we will start from the Dirac delta of x, and in particular, we don't think of this function simply as the Dirac delta. Let's think about a train of impulses like this. So we have a Dirac delta centered at x equal to 0, then we have a Dirac delta centered at x equal to capital T, and then we have another one located at minus t, and so on and so forth. So these impulses are periodic with period t, x equal to t. And we can represent such a function by using a Fourier expansion. So we will consider only the interval which goes from minus t halves to t halves, in which we have only this impulse, this Dirac delta. And if we expand this function in a Fourier series, then what we will obtain is exactly this train of impulses, because this impulse will repeat periodically in each interval whose length is t. So the length of this interval is t, right? So let's start. Now, what I'm going to do is I'm going to expand this train of impulses by using a Fourier representation, a Fourier series representation. So we have a summation with the index n going from minus infinity to plus infinity of some coefficients c sub n e to the I k sub n x, where k sub n is equal to 2 pi n over capital T, which is the period, so the fundamental period, which is exactly the length of the interval here. So T is the length of the interval. Now, this will be, of course, equal to that train of impulses, and in particular, we can simply write the function delta of x, because we are considering the interval from minus t halves to t halves, right? So we will only have the Dirac delta of x in this interval. Now we can integrate both sides of this equation. So we integrate from minus t halves to t halves, delta of x, and we multiply it by e to the minus I k sub m x dx. And therefore, this will be equal to summation from minus infinity to plus infinity c sub n integral from minus t halves to t halves e to the I kn minus km x dx. Now we have to calculate this integral here on the right. This integral will simply be e to the 2 pi I n minus m x over t divided by 2 pi I n minus m over t evaluated between minus t halves and t halves, right? So I've simply calculated this integral by substituting the expression for kn and km, which is given here, right? So this can be written like this. It's e to the pi I n minus m minus e to the minus pi I n minus m, and then we divide by 2 over t pi I n minus m, and this can be written as t times the sine of pi n minus m divided by pi times n minus m. So I have I've replaced this difference in complex exponentials with the sine multiplied by 2i. So I will get rid of this, and then I will be left with this expression, this simple expression. Now, it's easy to see that if n minus m is not equal to 0, then the sine of pi times an integer will be 0, whereas the denominator will be non-zero, so we can say that the result is 0 if n is not equal to m. Whereas if n is equal to m, or in particular if we consider a limit, it's easy to see that this will be equal to 1. It will go to 1. So it will be capital T if n is equal to m. Simple as that, right? And basically this means that this calculation is very simple. So this will give us T times C sub m, like this, right? So this integral here can also be rewritten as the integral from minus t halves to t halves delta of x dx, because we can evaluate this function at x equal to 0 since it is multiplied by the Dirac delta, so this will be equal to 1, and therefore we get a very simple result: c sub m is equal to 1 over t, right? And therefore this means that t times the train of impulses, so we can rewrite it as sum from minus infinity to plus infinity delta of x minus nt, because these impulses are centered at nt, if you think about it. So n can be 1, 2, 3, and also negative 1, negative 2, negative 3. So it is just an integer, negative integer or positive integer, not a problem. So we can rewrite it like this. And this will be equal to the formula that we wrote above, right? This formula here, where c sub n is equal to 1 over t, but I have already put t here on the left, so I simply have to rewrite the right hand side as summation from minus infinity to plus infinity of e to the I 2 pi n over t x, like this. And by the way, this formula holds also if you have a minus here. It will be exactly the same. So you can see that on the left we have something real, because this is just real. On the right we have something which is complex in general. So in order for this to be real, it means that this should also be equal to its complex conjugate. So we can rewrite everything like this as well: minus I 2 pi n over t x. Now if we choose t equal to 1, this formula will yield exactly what we are searching for. So the following formula: summation over n from minus infinity to plus infinity e to the I 2 pi n x equal to summation over n from minus infinity to plus infinity delta of x minus n. And if you want here, we can put plus or minus. So this is the formula that I wanted to get in this lecture, to obtain. And then we will move on. We will find other formulas, other interesting formulas, and we will use this formula in order to obtain an interesting result related to the analytic continuation of the Riemann zeta function.